We're going to talk about two problems today. The first problem is the double reflected light ray. Two mirrors make an angle of 120 degrees with each other, as illustrated in figure 37.5. My bad, little bit of a flipperoo. Figure 35.7a. A ray is incident on mirror M1 at an angle of 65 degrees to the normal. Find the direction of the ray after it is reflected from mirror M2. Problem 35.5. Measuring n using a prism. Although we do not prove it here, the minimum angle of deviation delta min for a prism occurs when the angle of incidence theta 1 is such that the refracted ray inside the prism makes the same angle with the normal to the two prism faces, superscript 1, as shown in figure 35.17. Obtain an expression for the index of refraction of the prism material in terms of the minimum angle of deviation and the apex angle phi. Holy shit, that's a crazy problem. Now, I said problem for both of these, but they're really examples in the book. If you go in the book, example 35.2 is almost the first example they give on reflection, and example 35.5 is one of I think it's the second example they do on refraction. And these are the two main concepts that you learn in this chapter, chapter 35. So it puts into play, it lets you practice with the law of reflection and the law of refraction. Now, to start off with this problem, I'm going to write down theta 1 equals theta 1 prime this is the law we're going to be using to answer this problem. So let's, in red, take a look at the problem here and quickly highlight what they're asking us. A ray is incident on mirror N1 to the normal. Find the direction of the ray after it is reflected from M2. Find the direction. Okay, here is M2, and here is the light ray. Theta M2 is the direction from the normal of this mirror to where the light ray is going. So if we find this angle here, I think we can solve the problem. In order to do that, we should draw a nice picture. So I'm going to slide down here and go boom, boom, label this M1, label this M2. Then I can use this red as the ray of light. So it's coming in from here, boom, and then I'm going to use this blue over here to draw the first normal. Now the problem already gives us an angle to work with. This angle is from the light ray to the normal, or from the normal to the light ray. It's the same angle, and they label this angle 65 degrees. Cool. Now, by the law of reflection, this light ray will bounce off at the exact same angle, 65, to the normal when it reflects from this mirror. So this angle here will also be 65 degrees. And that is the law of reflection. Now I'm going to approximate it here. I'm just drawing a picture. So the angle does not need to be perfect, but we can label it 65 because we know it's the same angle. Cool. Now, as you can see, the light ray is continuing here, and over here we have a different mirror with a different normal. Remember, normal is always perpendicular to the mirror or the surface is talking about. Sometimes they put arrows on these, sometimes they put the letter N or lowercase n, sometimes they actually put an arrow or a hat. Take a look at my vector video if you want to learn more about that. Not too important for solving this problem. However, we see an angle forming with this, and this angle is not given to us. Remember, over here, they actually label it theta prime M2 and theta M2. So we don't actually know this angle, but we can label it the same as the book, theta subscript m subscript 2, and by the same law of reflection that we used over here, we will use it again over here and see that this light ray bounces off somewhere in this direction. Let me redo this like this. Boom. And we have the angle which we are looking for. Theta m2 prime. It's going to be the same as theta m2. But how can we find this angle? Well, take a look at the whole picture. I'm going to take a sip of tea. Mint tea with some honey. Just keep looking at the picture. Don't even need to stress about any ideas or problem-solving strategies. Let yourself get comfortable with the picture. Maybe think a little bit. Maybe think about the warmth of your tea. You know, relax. The problem doesn't always have to be stressful. You know what I mean? You can just drink the tea and look at the problem. No stress needed. Got it. It's good. Mint tea. You know, coffee's good too. I like coffee. Water, very solid. Get some water. Okay. If you have no ideas, take a look at what we're looking for. We are looking for this angle here. If we don't know how to get this angle, we should look at relations and things that we do know. So for example, we know 65. We know M1 and M2 are at this angle, 120 degrees, which I actually did not write before. But if you reread the problem, you will see this is a piece of information given to us. And another thing we know is the normals over here are at 90 degrees. That's another piece of information. I'm going to actually write that in blue over here because the normal is in blue in my picture. But you can do it in whatever color you want. 90 degrees. Now, take a look at this. If we zoom in over here and we see that this is 90 degrees and this is the angle we're looking for, theta m2, then 90 degrees minus this angle here, right? We have this angle from the normal to the light ray, and we have this angle from the light ray to the mirror, or from the mirror to the light ray. We don't know this angle either, but if we did know it, we could literally just take 90, subtract that angle that we find here, and the answer that we would get is this. All right, so I'm going to write that equation down in the side over here. I will do 90 degrees minus question mark, and I'm going to call this over here question mark, equals theta m2. Now keep in mind, if we have theta m2 and we put a big box around it and we say the direction of the light ray, like this, we put a number in here, then we solve the problem. So we have this line over here, and let's keep working with it down here. How do we find question mark? Well, let's take a look at the picture again. And one thing that you might not know that is very important in this scenario is a small fact about triangles. So here I have a triangle, here I have another triangle, and here I have a third triangle. All these triangles have interior angles A, B, and C, right? They could be different angles, but you could label each of these angles with some letter, whatever, you know. You don't know what these angles are, but you could just label them as variables A, B, and C. One fact about triangles, and this applies to all triangles, is if you sum up all of these guys, all the angles on the inside of a triangle, you get 180 degrees. That's pretty wild. And it's pretty strange. And if you want to know where this comes from, you can dive into some crazy math. So maybe search up online, why do all interior triangles angles, why do all the interior angles of a triangle add up to 180 degrees? And you will get into some crazy math, some ancient math. You know Pythagoras, our boy Pythagore. This guy lived so long ago, bro, and he thought of this shit. So you can dive into that if you were interested. Here's a couple pages on Wikipedia of interesting stuff you could take a look at, which is mildly related to this. And yeah, you might be quite interested in this field of math. But for now, don't stress about all of that. All you need to know is this identity is true for triangles. All triangles. Any triangle you can think of, if you know it's three angles, you can add them up and get to 180. But if you don't know the three angles, let's say you only had this one and this one, you could use this relationship to isolate for the missing angle and determine what it is. How do you do that? Well, you know B, you could just subtract B on this side, which cancels it here. If you know A, you could subtract A on this side, which cancels it, and you have an equation for the remaining angle C. 180 minus whatever B is, let's say it's 90, minus whatever A is, let's say it's 20 degrees, and you'll get an answer for C, and that is always true. Maybe not always, maybe not in all scenarios, but in pretty much all scenarios that you work with on a piece of paper, on a flat surface, you're going to be chilling. So, knowing that piece of info, let's take a look at our setup over here. And knowing this piece of info, you should look at any triangle that appears to you. So, personally, I see a weird triangle right here. I see another grandiose triangle right here. Another triangle maybe right here. Another triangle right here. And this triangle here is going to be super important. Why? Because we are looking for question mark. If we find question mark, which is this angle here, we can plug it into this equation, which gets us this, and this is the solution of the problem. So take a look at this triangle right here and apply this equation to find the question mark. So we already have 120. That's literally a definition from the problem. All we need is this angle here, and we can subtract this and subtract this from 180, and we can find question mark, and that will get us the solution. So that might have been a crazy pathway, and you may have not really known how to solve that unless I told you this piece of information here. But that's the whole point of physics problems. You don't learn this piece in the class, but you might come across it if you're solving the problem in the strategy that I just recommended here with the triangle. So there's many different ways of attacking a problem. Maybe in a problem like this, there's, few ways, but each problem may have several different attack strategies. And if you try it out, you might learn something new. And if you learn something new, you could just remember this for future cases and use it if you want. That's the beauty of math. It's like a bunch of tools in a tool bag. Very useful. Okay, so you know this piece of fact that I used over here, which was 90 minus this angle over here, will get us the remaining angle, which is this one here. I'm going to use that same piece of info here. I have 90 degrees, which is the normal. From the normal to the mirror gives us 90 degrees. And I can subtract this angle here from the normal to the light ray. If I subtract 90 by this, I will get this angle here, which is from the light ray to the mirror. So I'm going to do that, but first I'm just going to clean up my paper. This is a piece of useful info, which I will hold down here, but I kind of just want a little piece of room over here to solve the problem that I was talking about. So I can maybe draw like a scrap triangle like this. This angle here is 120. This angle here is the question mark we're looking for. And this angle here, let's call it X. I said 90 minus 65 equals X. And where did I get that from? Take a look at this area here. We have 90 degrees. we have 65, and over here is the x. So let me remove all that to not complicate the figure that much. And we could just do 90 minus 65. Hold it down. 65 to 70 is 5. 70 to 90 is 7, 8, 9, 20. So we got 25 degrees here, I think. Right? 5 plus 65 gives you 70 plus 20, 70, 80, 90 gives you 90. Okay, this I think looks good to me. Sorry guys, you gotta double check this algebra stuff. Sometimes, high level physics, it includes some crazy math, all right? And I urge you not to use a calculator, even for simple things like this. Use your brain. It's gonna scratch a nice little itch. The math itch. You'll be bulling. All right, so what were we doing here? X equals 25. So I can use that triangle identity, which is 180 degrees equals 25 degrees plus 120 degrees plus question mark. And I am looking for this question mark. So how do I solve this? I do 180 minus 120, minus 120 minus 25. And this will give me question mark. So I have 180 minus 120, that gives us 60, right? 60 minus 25 gives you, 60 minus 20 is 40, minus 5 is 35. Is that true? 35 degrees, question mark equals 35 degrees. I will just write that here. Oh wait, my bad. That one actually equaled 25 degrees. That was x. So you see how if you just draw a bunch of pictures, you might get a bit confused here. Try not to do that. Keep things as simple as you can, or at least try to follow them along. As you're doing the problem, you'll have your own different strategy and layout of how to write things. So make sure to follow it and not confuse yourself. There's quite a lot of angles now happening, but question mark is 35 degrees, and that's the thing we were looking for. So now that we have question mark, we can do 90 minus question mark, which is 35 degrees, and that'll give us theta m2. So 90 minus 30 is 60, right? Yes. Minus 5 is 55 degrees. Okay. So I think 55 degrees is our answer. All right. Does that make sense? I mean, I guess. How do I check it? Is there any way to double check if my answer is correct? Well, it's an example in the book. Perhaps we can take a look at the book, and the book gives us a final angle of 55, and they color it in blue. All right. Nice. So that's good. We got the right answer. Well, I'm not going to read through this example, but if you're interested, this strategy might be a little different. It looks like they have angle delta and angle gamma, which is the same ones that we were looking for, except we labeled them differently. And it looks like they use the same trick of adding up all the interior angles of a triangle to make 180 degrees. So the first thing I'll start with here is n1 sine theta 1 equals n2 sine theta 2. And this is called Snell's law, or law of refraction. So this is quite important. And if you don't know about this, and this doesn't spring out at you at the first moment of seeing a problem like this with different angles and light rays entering different mediums, I would say read up about the theory a little bit. Take a look at my previous video where I kind of zoom through the chapter. And if you're also interested, take a look at some videos online about Snell's law, the law of refraction. It's kind of just given to you in this moment. We don't derive it. We don't talk about where it comes from. We just use it. And that's one area in physics where you use a law to solve a problem. Another area, though, is researching where the law came from, or trying yourself to derive that law from previous principles which you believe in. So right now, I'm just giving you Snell's law, and you might be like, hold up, I don't even believe in this, bro. And that's a great feeling to have, because you're questioning, you're wondering, like, bro, you just gave me this equation, you're like, okay, it's going to be used to solve the problem, but why? Like, are you confident? Well, one way to be confident is to use this law, solve the problem, and see if you get the right answer as the people in the book. But that's quite, I wouldn't say boring. It could be pretty fun, but it's a little bit like walking in the fog. Like, you don't really know if this is the right way to go, to move forward. So a way of alleviating that is by reading a bit of the theory, where this comes from. Uh, while you're reading the theory, you could actually see a little bit of why it was, um, why people came about this law, why it's true, how it could be derived, how you could think of it in different ways, where it came from. And perhaps it could convince you a little bit more. You could believe in it a little bit more. Or you'll just be a bit more doubtful, like, yo, where is this coming from? I really don't feel comfortable with this equation. Like, I'm not sure it's the right way to move forward. And that's why I think it's a great feeling to be doubtful of this stuff, because that's how scientific discoveries are made. Like, you straight up gotta question somebody else's work, somebody that you think was unbreakable. Like, once you get to some of Einstein's stuff, or any big physicist that drops some law, you still gotta question it. You can't just be like, oh yeah, I believe this because that guy did it. You gotta check their work. So, a little bit of a ramble here, but we're gonna start with Snell's law. And why is that the case? Because we have a light ray, in this case, this blue light ray, which is coming in over here. It is refracting over here, and it is continuing over here. And that's happening because this prism here is a different medium. You can see it's colored blue. They actually, in this problem, they ask for the refractive index. And that's the thing that led me to this equation, because the refractive index is right here and here. This is refractive index of the outside medium. So this stuff here, normally it's air, which has refractive index of 1. And normally this one is the secondary medium where your light ray is refracting into, which is actually what the problem is asking us to find. So this law jumped out at me because, one, it's related to the theory I read about, and two, it actually includes as a portion of itself the answer to the problem we're looking for. So that's another great thing, and something that you might think about when you're reading problems. You could be like, yo, I already know an equation that has what I'm looking for in it. So I could use that, and maybe it could be helpful. Who knows? Maybe it won't be helpful, but throw it out there anyway, like write it down. So I wrote this one down here, and I'm just going to check what the problem is asking me. Obtain an expression for the index of refraction of the prism material in terms of the minimum angle of deviation and the apex angle phi. So in these cases, I like to draw my own picture just because there's a lot of moving pieces and I would like to label things in my own way. So I have a picture of the prism here. And I can already see what the apex angle is. It is this angle over here. You can see actually they cut this in half and then they measure this angle and they call this phi divided by 2 right here. So that means this whole angle here is phi divided by 2 times 2. The 2's cancel, so it's all of phi, the apex angle. But I remember the apex angle was also introduced in the section just above this in the textbook. So take a look at that if you're a little bit confused of where this is coming from. So in this case, there's no numbers, it's just symbols, which is okay. It's actually very fun working with symbols. There is one number, and that number is 1. This is the index of air, which is all outside here, and that's just an assumption. You can read about that also further in the book. So what we're looking for in this scenario is the index of the glass, which I will call NG, index glass. This is question mark. So I have index of the glass. So if I put a box around this and right underneath it, I call this um, index of refraction of prism, and I put some stars around it, I think I will be able to solve the problem in its totality. Cool. So it's asking us to find that in terms of the apex angle and the minimum angle. So let's draw the light ray in this red color. And as you can see, it's going like completely horizontal over here in this section, this way. But then over here, it refracts like this. And over here, it refracts like that. That was a curved line that did not look the best. Refracts like that. And there's normals over here. So there's a normal right here, like this. This is normal to the prism surface. And this is normal to the prism surface. And they give us a couple more angles. I will draw these in, let's pick a cool color over here, yellow. Let's go with this little yellow color here. They actually label this theta 1. And this is also theta 1, interestingly enough, the same angle. All right. And then we got some more dotted lines. I'm going to draw these dotted lines in this dark blue since I have not used this color yet. So this dotted line looks like it's a continuation of this light ray. And they call this angle here alpha. Then we have a continuation backwards of this light ray, like that. I don't know if this is perfectly symmetric, but they call this alpha as well. Then they have this straight line here. This is why I knew this was not symmetric. It's supposed to attach right here. So maybe I messed something up with my lines, but we got this over here, and then we got this angle here, which is 5/2. I'm not sure if that's important. Let's do that in yellow so that we can see all the angles in yellow. And then we have this angle over here, which they call this. Okay, that's my own picture of this. It's cool drawing this. You might get a little better at drawing after you do it a couple times. So there's that. Oh, there's a couple other angles, theta 2, that I didn't draw. Damn, that's gonna complicate my picture. Let me move this over here so I have some more room to work with. I'm gonna draw this. But what even is that angle, theta 2? What is the point of that angle? Oh, I guess that's the normal. So the normal continues on the inside of the prism here and on the inside of the prism here, like that. And then these angles here from the light ray, theta 2. From the light ray to the interior normal is theta 2. Okay. So why is all of this even useful? It's asking us to obtain an expression for the index of refraction of the prism material in terms of the minimum angle of deviation and the apex angle phi. Broski. What does that even mean? Okay, let's use Snell's law. Okay, so let me simplify the triangle, or the prism a little bit more like this, and redraw the light ray. So I have a light ray going in like this, boom, and then it refracts here. So keep in mind Snell's law is looking for this first angle from the normal to the light ray. So this angle is theta 1. And remember, N1 is index of air, which is just 1. So we have theta 1 over here. So if we have Snell's law, that's straight up the first stuff that enters there. Sine theta 1. So we have those actually. The second part of Snell's law is N2, and N2 in this case is actually N glass, right? That is straight up the definition of Snell's law. It is n1 sine theta 1, so index of refraction of the first medium, which is air, sine of theta 1, and theta 1 is the angle at which the light ray makes as it contacts the intersection of the two mediums, n1 and n2, in this case the prism. So that angle to the normal is theta 1 over here. N2 is actually the thing we're looking for. So in the equation we have sine theta 2, but I'm literally just going to take this and divide it out onto this side. Why am I doing this? Because now if I rearrange this onto this side and move this here, I obtain an expression for n glass. I'm literally going to replace this with n glass. And remember, this is the answer. So if I plug this back into there, I should get the right answer. You guys see how I just used Snell's law to find an answer for the index of refraction of the glass of the prism, but the problem isn't solved yet because it says obtain an expression for the index of refraction of the prism material in terms of the minimum angle of deviation and the apex angle phi. So I haven't done that yet. It says in terms of, that means this thing should be created from the things that it's talking about. So minimum angle of deviation and apex angle phi. In this case, I have n1, which is neither of those, theta 1, which is neither of those, and theta 2, which is neither of those. So the problem is, theta 2 actually, is that theta 2? Let me just draw this because Snell's law helps us find this theta here, theta 2. And let's take a look in the picture if we have that. We do actually, we've labeled that theta 2, right? That is the light ray going here, boom. This is the interior normal to the prism surface, and they actually also label this theta 2. So the question is basically asking us to somehow now replace theta 2 and theta 1 with the angles phi and this minimum angle of deviation, delta min. So how do we do that? I mean, we have to find a way to like break stuff apart and find relationships between the angles. And it looks like it's gonna be quite annoying. I'll be real with you guys. I actually have no idea how to find it. So let me just take a look at this problem for a minute and just stare at it. All right, so remember our objective. If we find an expression for this and plug it in here, we answer the problem. The only thing is, we do have an expression for this, except we want to replace theta 1 and theta 2 with these two different symbols, apex angle phi and minimum angle, which is delta subscript min. If we find a way to replace these two symbols for those two symbols, and we plug that into here, then we solve the problem. So our objective is this, and I'll write it down over here. Find theta 1 and theta 2 as functions of apex angle phi and minimum angle. Or if that's too complicated, basically replace this or find an equation, equal sign, where this thing over here has phi and delta min in it, right? These two expressions are equivalent, and that's what we want to do right now. So there's two ways I see, two kind of strategies right now that I was thinking about, and that is start with this symbol and try to find a pathway to these symbols, or start with these symbols and try to find a pathway to this symbol. What does that mean? Well, look at our picture over here. This is all the stuff that is known from the problem. It's given to us. And we have this over here, theta 1 and theta 2. And we also have phi and delta min in here in the same picture. So we just kind of have to find a couple of relationships like this and like this through some triangle identities or through some angle relationships, and then we're good to go. But it's a complicated picture, so you kind of want to start somewhere. I would start here and then build my way up to get this and this included in the equations, and then I'll go on to this thing over here. But you might see the problem a little differently, so feel free to attempt anything you want here. All right, so I will start here with theta 1 equals, and I want to find some kind of relationship which changes theta 1 into something else in the picture. And I will do this by duplicating the image and pasting it over here and just making it a bit bigger. Do I have enough room here? Yes. I'll just take this stuff, move it kind of in this corner, and then take my big picture and move it like right here. Let's chill with everyone. Alrighty. So let's find theta 1. Theta 1 is over here. It is the angle that goes into the first part of Snell's law, the angle from here. So I'm going to take a look at just the triangle overall, and what I see first is this straight line here and this straight line right here, and they intersect at this point over here. That's the only thing I'm looking at. Why am I looking at this? Because I know these two things are straight lines. From here to here is 180 degrees, right? That's the kind of a definition of a straight line. And same thing over here. So whenever I see this, the main thing I think about is this angle here must be equal to the opposite angle here, whatever this is. We'll call it theta 1. And this angle over here, let's call this x, must be equal to this angle here. You could think about this with any two crossing lines. Think about this. Two intersections. Right here is a right angle triangle. Or sorry, right angle, right angle, right angle. All of these are 90 degrees. Why? Because I see the straight line from here to here is 180 degrees. And if you cut that perfectly in half right in the middle, you have two equal portions of 90 degrees here and 90 degrees here. And same thing over here on this side. This is 90 degrees. This is 90 degrees, right? And if you take one of the lines and slightly put it on an offset, you still have the same principle. This whole thing here is 180 degrees, but this angle here, let's call it x, is bigger obviously than this angle here. We can call it y. But you do know that these two add up, so we could do x plus y here to get you this 180 degrees. And because of the symmetry of the two lines, on the opposite side, you must have the same relationship, but flipped. This is the bigger x angle, and this over here is the smaller y angle. And both of these still add up to get you 180 degrees on the other side of the line. So any type of intersection between two lines, it could be like this. You know these angles are the same, and you know these angles are the same. The lines could be in any which way, like this. You know this angle here and this angle are the same, and these two angles are also the same. So that is something I see over here. And why am I doing that? Because I can then find an expression for this in terms of whatever is inside this angle, right? Because we just said this is an equality. So inside this angle is alpha and theta 2. So straight up right over here, alpha plus theta 2, and I can prove this by that little like analogy I made with the two lines. You could make some other arguments, and you'll see this is where it comes like it's a bit handy to have a couple tricks up your sleeve, stuff like this that you're kind of confident with proving or believing in fairly quickly, but you'll learn more as the time goes on. So maybe one thing you can think about now too is this straight line over here. You can see it is intersected by another straight line here. And this angle here is pretty important to us. It is the delta min angle, which we're looking at. The thing I see here is this angle and this angle can combine. We have a straight line here. You know from here to here is 180 degrees. And a portion of that 180, this portion right here, is the delta min angle. So the remainder of the portion here, if I know that, I can take this remainder, let's call it x, and do 180 degrees minus x, and that will give me delta min. Okay, that's just kind of stuff that's popping out at me. Similar kind of thinking process as this thing, this little x over here where these angles are similar. So if you see that, maybe you can take a look at this triangle here and it could help you determine this missing angle. And once you know that, you could then replace this delta min. But I don't know if that's even too helpful for me. Is that helpful? I'm trying to find a way to make these expressions equal into these. And right now, all I have is alpha over here. Oh, but look at this. Alpha actually goes into theta 1. So if I find this in terms of alpha, I can just replace alpha and then I have this inside my equation. So that actually knocks out this thing here. So that brings me one step closer. So I don't know if you saw what I was thinking of there. I was trying to kind of put it into words, but basically I'm just trying to check if the work that I'm going to go through right now, which is the thing I talked about over here with finding this angle in terms of this, and then finding this angle using this triangle here with these angles. I'm just trying to see if that's going to be beneficial for me in the future. And I think it is. So what I'm going to do is find an expression for this. I will put it in a crazy pink color. So I want to find this angle. Let's call this x, right? And I'll draw this in pink right here. X is equal to 180 degrees minus alpha, which equals to 180 minus 2 alpha. Some simple algebra there. And why is that the case? Because remember that triangle identity I talked about. All the interior sides of a triangle add up to give you, this is an x, 180. So if I have alpha plus x, I know that equals 180. So here I have 180, and I already subtracted these two alphas on this side. But if I move them back on this side, I have basically, here I have alpha plus x, and that gives me 180. So that is that triangle identity used to find what x is. 180 minus alpha. I combine the two alphas together to get minus 2 alpha. Okay, now that I know what x is, I'm going to use this angle here. Let me pull up an orange color. This angle here, which I know is 180 degrees. All right, and with this orange, I have 180 degrees is equal to x plus delta min, which means I'm going to put an arrow over here. Therefore, maybe I'll write that. Delta min is equal to 180 minus x. Is that true? So another arrow. I'll do delta min is equal to 180 degrees minus, and I have x over here in terms of 180 degrees minus 2x. So I'm going to put some big brackets over here. 180 degrees minus 2 alpha. Maybe that looks too much like an x, so I'm going to do that. And then I can simplify this by removing the brackets. So 180 minus 180 actually cancels out. Boom, boom. And if I do, wait, does it cancel out? Yeah, I think it does. But then I have 0 minus 2a. So the whole expression here is minus 2 alpha. So I have a new expression for delta min is equal to 2 alpha. Okay, so why is that useful? Well, let's go back over here to look at the first thing we started with, which is theta 1 is equal to alpha plus theta 2. So now if I divide 2 onto this side, I have alpha is equal to 1 over 2 delta min. And I can now take this and plug it into the thing I had up here, right here. So I now have theta 1 is equal to 1/2 delta min plus theta 2. Okay, I know that seems like a whole bunch of nothing, but pretty useful identity. You know what? In fact, I'm going to put this in a red box because I think it's useful. I think we're going to come back to this bad boy in a second. All right, now let's take a look at anything else we could do here. Well, I haven't used this identity here, And I want to find a way to bring this into this equation or somehow use it here. So I'm just going to see if I can work with it in any which way. So what I see is a triangle over here, which actually has one of these phi's in it. This angle over here is equal to phi over 2. Right, that's a definition from our original picture. This angle here, phi over 2. That is because the whole apex angle here is equal to phi. And actually, they use phi in another place over here. So if you're interested, you don't have to look over here. You could look at this angle and try to make some stuff happen here. But I'm going to start with this over here. So let's take a look at what we can do with this. Again, I'm looking at this over here. So maybe I could look at this big triangle here. Why am I doing that? Well, if I know this angle here is phi over 2, then I could maybe plug that into here, because take a look at this. If I'm looking at this triangle here, I want to find this angle here, right? If I have this angle, I can use it to relate to this angle. I mean, I also need to find this angle too, so that would be a bit interesting. But this angle from here to here, I think we could find it in some way. How can we find that angle? Let me think. Okay, I have an idea. I'm going to redraw the triangle to make it a bit more simple. So I have this complete vertical bisection here. And let me take a look at the original picture. I have the incoming light ray, which is going like this. The light ray refracting and going like that. And then the outgoing light ray, like this. And they intersect like that in the middle. Okay. So we have this angle over here, which is phi over 2. And we have, let me look at the picture again. The angle from the normal here to the light ray. Or no, from the light ray to the other light ray. Okay. From the light ray here to the other light ray. This angle is that true? It appears to be. And actually, we also have this angle here. This is x from the previous time we were looking at it over here. So this is actually coming in useful. And the only thing I'm thinking about is if by the symmetry of the problem over here, no, actually that's not useful. So what we're looking for is this angle here. Let's take a look. Alrighty. So I'm going to actually erase a little bit of this. Erase all of this right here. Zoom in and erase this. Okay. This is what the picture is looking like. So we have this angle over here of this big triangle. And why am I looking at this triangle? You'll see in a second. I want to find this angle and I want to find this angle. So if I want to find this angle first, I have from here all the way to here is 180 degrees. From here to here is half of x. And from here to here is the angle that we're looking for. So I have a way of finding this angle. I'll write it down in a equation in a second. But that means if I have this angle and this angle, I can find this angle over here. And if I find this angle, and this angle includes a theta 1 in it, then I've effectively found a way to relate phi to theta 1. So I'm not sure if you see the same thing I see over here, but we will work with that for now. So let's begin with finding this angle here, which I will actually draw in blue and a bit of yellow like this, and we'll call this Z. Because I am running out of letters, we'll stick with Z. So I want to find Z. All right, and how do we find Z? Well, I will do Z is equal to, So take a look at what I'm thinking about here. If I start measuring over here and I go all the way around, this is 360 degrees, right? This is the complete loop-de-loop. It's how we've defined angles. A total loop around like that is 360. If I do 360 minus this, we will call this exclamation point, whatever. We subtract this, we already have a symbol for that, and we subtract this, the symbol that we found in the previous part over there. If we subtract all of those from 360, then we can find Z. Do you see what I'm saying? So I'll do 360 minus, let's actually label this as an angle over here. Exclamation point, that's a little bit weird. Let's use, symbol. Let's use gamma. No, that one's goofy. Let's use, this is tough, bro. What symbol do we use for this one? I don't like exclamation point. And you know what, brother? Let's just use the number sign, okay? Number sign angle, let's go. We have 360 minus number sign. I'll do that in blue, and then I'll minus delta min minus x. Okay, so this is truth right here. This is truth. I have proven it to you guys by just talking. And again, if you don't believe me, you gotta Google search some stuff about like those angle things I was talking about earlier and see if you can convince yourself in other means. You could just sit with a piece of paper and a protractor or a compass, either one of those, and see if these things are true by working it out on your own. But I'm going to make this claim right now. So, okay. The problem is there's a couple of unknowns here. Well, first of all, the only unknown that I think is this one here, because we found x before, right? X equals 180 minus 2 alpha. So, you know what? I'm actually going to move on with this 360 minus, I'll still do this in blue because it's kind of the main unknown, minus delta min, and we want to keep delta min. Delta min is what we want to work with because our solution will be in terms of delta min. X is 180 minus 2 alpha. So I'll again do brackets, 180 degrees minus 2 alpha. We can replace alpha, but let's do some simplification here. So I have Z is equal to 360 degrees minus 180 degrees. We'll do minus, so here there will be a plus 2 alpha, minus delta min, and then minus, I put this symbol here at the end. I kind of just moved some stuff around. And the reason I did that is because we can simplify this, because these two are just degrees. Everything else is kind of variables and unknowns, so we can't really simplify that. 360 minus 180 is 180. Then here we have plus 2 alpha minus. All right, unfortunately, my microphone passed out here, so I am re-recording after the regular recording. So some of the things I say here might be a little bit behind or delayed, but I'm gonna just follow up. So what we're doing here is finding Z. I simplified, and here I'm trying to plug in alpha, which we found from the previous part. You saw alpha equals 1/2 delta min. So we're replacing that and following through, and it looks like I made a small mistake here, but I haven't noticed yet, so we're canceling out the 1/2 with the 2 over there because we have a 2 alpha, and the alpha itself has a 1/2 in it. So here I'm fixing the mistake. I forgot the delta min minus delta min from the previous part, and I am just replacing it back. Nice. So now that we have all of that, over here I'm just showing how I simplified that. I carried the 2 alpha, I carried the minus delta min, and I carried the minus blue hashtag. Then I replaced this alpha with the alpha we found above. 1/2 delta min is equal to alpha, and alpha is being multiplied by 2, so that 2 cancels with the 1/2. And since I carried this original delta min and this hashtag, we get the final equation, and we can simplify it a little further. So it looks like here there's a plus delta min and a minus delta min, and they cancel perfectly. At the end of the equation, we have the minus blue hashtag. And we can just simplify the equation for Z as much as we can here, which leaves us with 180 minus blue hashtag. And the blue hashtag, we still actually don't know what it is. So this equation here is a little useless unless we find a way to relate that blue hashtag to some other variables that we know. So here I'm looking at the original triangle, and Z is over here, this angle, and hashtag is the one over here. So it's kind of like we have two unknowns. What I would like is to find Z completely in terms of phi and delta min, but I first have to find what this blue hashtag is, which is gonna be kind of annoying. So here I'm showing, I guess, all of the interior angles of that triangle, and I'm trying to think about how this is useful, and I'm showing here a 90-degree angle. This 90-degree angle is comprised of theta 2 and alpha, and we can actually use that to later combine or find a way of writing theta 2 in terms of phi over 2. And then we can plug theta 2 into this equation and find a relationship for theta 1. And then theta 1 we can plug into our original equation here to get the index of refraction of glass, which will answer the whole question. So at the end of the day, I'm just trying to find theta 1 and theta 2 in terms of phi and delta min. So we're going to go back to this original equation. As you can see, I got left at Z, but I'm going to keep looking at this triangle here. That is the Z that we're just now trying to find right here, and it is literally equal to 180 minus hashtag. So how can I find this hashtag? I'm going to take a look at this bisector over here, which completely cuts the triangle in half, and from one side to the other of the bisector gives us 180 degrees, as you saw there. This 180 degrees is comprised of 3 different components, one of which is the blue hashtag. The other one is the delta min, and that tiny component there looks like it's about half of x. That's the full x there. If we divide x by 2, we get 1/2 x on this side, 1/2 x on that side. If we add them together, that gives us the full x, which is right here. And we actually have x in terms of 180 and 2 alpha. So I'm trying to see here if we could use that, but anyway, I'm just going to take a look at this 180 degrees, split it up into these 3 components, and then we can maybe use that to find what blue hashtag is in terms of things that we care about. So I'm going to write over here blue hashtag, little colon, little underscore to show that we're going to solve for it here. I'm going to start off with the identity that I discussed, which is 180 degrees I can split that up into half of x, split it up into delta min, and split it up into blue hashtag. So 180 degrees, we break that up into 3 different angles, 1, 2, and 3 over here. And we can see those 3 angles right here. 1, that's the half x, 2, that's the delta min, and 3, the blue hashtag, which is what we're looking for. So since we're looking for the blue hashtag, I'm going to isolate for it, keep it on the left-hand side of the equality here, and I'll get 180 degrees minus 1 half x minus delta min. Looking good. And delta min we can actually keep. Delta min is what we need to give our final answer in. So I'm going to take a look at what x is, and it's 180 minus 2 alpha. So x is in our equation here, which will let me simplify it a little bit more. We got 180 degrees, stays the same. 1 half, open bracket. I'm going to put in that x, which is 180 minus 2 alpha. Remember, we found that from the previous section. And then I carry over that minus delta min. So we can simplify a little more. We're going to rewrite this 180 degrees. Then we can distribute this 1 half. So 180 divided by 1 half should be 90. And then that minus 2 cancels to give us just minus alpha. Outside the brackets, we have still the minus delta min. We could subtract 180 minus 90 here. And then minus alpha gives us plus alpha. Then we still carry over this minus delta min. Looking good. So 180 minus 90 will give us just 90 degrees. We can write this down here. $90. Checking to make sure what alpha is. Replacing that with 1 half delta min. And then I can carry over this final negative delta min. So if I have a plus half delta min minus delta min, I will just get a minus 1 half delta min, right? I have negative 1 of the full thing plus half of the full thing. It'll just give me negative of that full thing. So that, I think, simplifies the hashtag as much as possible. And we can finally plug it in here, and we'll obtain a final expression for z, which will be 180 degrees. We got the minus 90, and then minus gives us a plus 1 half delta min. So we'll simplify this one last time. 180 minus 90 gives us 90 plus 1 half delta min. And since this is the final form of this z, and it should be quite important, I'll just put a little box around it right here. Looking pretty good. And we can relate this to what the bigger picture is. Looking back at the picture and looking back at where z is, I'm just going to rewrite this to take a look at the bigger picture. So this is the interior normal, exactly where the light is intersecting the medium. And as you can see, I'm breaking apart this 90-degree angle in terms of 3 angles. One right over here, which is part of this bigger triangle. And we could use z and phi over 2 to actually find this final angle of that triangle. It's literally 180, minus phi over 2 minus z. Then we have that middle angle there, which is alpha. We already have alpha in terms of delta min. Then we have this final angle here, which I believe is theta 2, as you can see here. So this is that 90 degrees. You can break it apart into all 3 of these angles. And this was the bigger picture I was looking at before. Again, the final objective is to combine all of these things and find an expression for theta 2 so that we can finally plug it in to theta 1 and then replace theta 1 in the original equation to get us the final index of refraction. So back to the original picture. What I need to find now is that final angle of the triangle, which includes angle Z and angle phi over 2. Then I can subtract all of those angles from 90 degrees. And it looks like at that point, I should be good. So I'm just going to cut here real quick and rewrite this in mathematical notation. So 90 degrees, this is comprised of theta 2 plus alpha plus the final angle, which I have not labeled, I don't think. Let's zoom in here to actually label it. It's this angle here. I'm going to just call it exclamation point. No better symbol than the exclamation point, and I read an I over here by accident. So we got three angles, they combine to give us 90 degrees. One of the angles we just spent a long time finding. Actually, no, we haven't even found exclamation point yet, but we know we could use Z to find exclamation point. So that's what I'm about to do right now. And alpha, like I saw up here, I have already obtained alpha, and I have already obtained, well, I don't have theta 2. I'm trying to determine what theta 2 is here. So we can zoom in and start working. I'm going to isolate for theta 2 because that's the thing I'm looking for at the end of the day. So we got 90, subtract an alpha, subtract an exclamation point. And here I can replace what I already know, which is alpha. It is 1/2 delta min. I know that from this upper section here, which I've been using so frequently that I just memorized. Then the second thing is this exclamation point. So let's use this triangle here along with that fact from previously in the video, which is all interior angles of a triangle add up to be 180. That means 180 is equal to exclamation point plus phi over 2 plus Z, which is the angle we spent all that time previously looking for. So I'm going to isolate for exclamation point here because that's what I'm looking for. This gives us 180 minus phi over 2 minus Z, which is 90. I'm going to do brackets over here, or I guess I don't do the brackets. I just distribute the minus sign to both. So it is getting a bit cramped over here, but no stress. We're going to simplify it right now. We got 180 minus 90 will give us just 90 degrees. Keep that phi over 2 with the negative sign, and keep that delta min over 2. I changed the notation here a little bit. So we have an expression for exclamation point, and I'll just replace it over here in the following line. I got a minus sign. Whoops, sorry about that. Let me fix this. Minus open bracket, plug in all of exclamation point, which I'm just double checking here is 90 minus phi over 2 minus delta min over 2. 90. We got minus phi over 2 minus delta min over 2. Close bracket, and I can simplify this a little bit more. So those 90s cancel. This leaves us with 1/2 delta min with the minus sign. We got minus minus, which makes a plus phi over 2, minus minus, which makes a plus delta min over 2. Looking pretty good. These delta mins cancel perfectly because we have plus 1/2 minus 1/2 delta min. So we just get theta 2 is equal to phi over 2. How interesting. Cool. So now that we got this, I'm going to put a box around it since it's important, and I'm going to just bring it all the way up to the top of this equation. One of the first equations, and I'm going to just write theta 2 is equal to phi over 2. Now I can just box this and plug theta 2, just double checking to make sure everything looks good. I could have made a mistake here, but I will hope I haven't. So we got theta 1 is equal to 1/2 delta min plus 1/2 phi And I am just combining the things that I found previously in the red box with what I currently found in the blue box. And I'm going to put a big, interesting looking red box around this because it is an important equation which we will use right over here. We could literally plug it in to this answer here. What we also need to find is theta 2, but remember this box from before? It actually relates theta 1 to theta 2. Theta 1 is right here. We could just plug that whole thing and isolate for theta 2, and we get theta 2 in terms of delta min and phi, which is exactly what we were looking for. I'm going to clean some things up over here and just write below here equation isolating theta 2. So we got theta 2. It is literally theta 1, so I'm going to copy it exactly what's in the box above here. 1/2 delta min plus 1/2 phi. That is exactly theta 1, everything you see here after the equal sign. And then I will just subtract this 1/2 delta min from the previous boxed equation, which you see up here, this one. So I'm going to put a big blue box around this one because that completes our collection of theta 1s and theta 2s. And looking back at the original equation, we can just plug in those expressions for these circled theta 1 and theta 2, which is what I will do right now. After I clean up a little bit, I'm going to move this thing up here, do an equal sign, and glass. That is what we're looking for. We got N1, which is 1. It's the index of air, so it doesn't really matter. The important stuff is what follows. So sine of theta 1, I have delta min over 2 plus phi over 2. 1/2 delta min plus 1/2 phi. Cool. Put that right there, close brackets, and then on the denominator we have another sign, except here we have theta 2. And I can actually simplify this theta 2 a little more. We got plus 1/2 delta min minus 1/2 delta min. Perfectly cancels, leaving us with just 1/2 phi. We put a phi over 2 over here, close brackets, and that is looking good to me. So I'm actually just going to move this over here to the side and fill up this little box, even though I'm just copying the same thing I have down here. But I want to keep it like this. So N1 again is just 1. So if I have it there, I can replace it with 1. I can keep it as N1. Doesn't really matter. Rewriting everything kind of cramped over there, but whatever. And I just want to make sure if this is actually correct. So I'm going to put a big box around this one and take a look in the book very quickly. So it looks like what we got is over here. Index of refraction is equal to sine phi plus delta min over 2 over sine of phi over 2. So it looks like the same thing. It's just we did not remove N1 index for air or we didn't replace it with a 1. And we also didn't bring the argument of the sign in the numerator to common denominator. So they brought the delta min and the phi, both of them divided by 2. They brought them together and put both of those divided by 2. I just kept them as separate, 1/2 delta min plus 1/2 phi. So looks good. Amazing problem. I know this video was very long to listen to, so if you have any questions or if you spot any errors, please drop a comment. If you have any other problem solving recommendations, let me know. I can do them on this channel if you want. Appreciate it. Have a good night and stay hydrated. Peace out.